All right, so I decided to go through an example with the projection. This is a very concrete example. I mentioned before that I like to use these set notations for subspaces. So if you have two subspaces U and W such that the whole plane is right now, then V equals to the direct sum of U and W, then it's kind of hard to work with projections because we don't really know what these U and W subspaces are. It's much easier actually to work with what I mentioned before, two-dimensional Euclidean space R2. So let's have the two-dimensional vector space xy, standard coordinates. That will be the V space. I'm not going to use the x and y axis for subspaces because that would be too trivial, and actually they will be used later for the orthogonal projection, but we are now working with general projections. So instead of that, I will look at two subspaces. One is written as x2x, where x is any real number. The other is w. Let's say x3x, where x is a real number. Well, what you see here is that U subspace is actually the line y equals to 2x, and W is the line y equals to 3x. Well, it's not equality because that's not a set notation I'm using it. I'm just writing it down now verbally. Y equals to 2x line and y equals to 3x line. So something like this. U and W. We also have to practice the span notation and not to confuse a vector with a subspace. Please pay attention to this because there were too many problems with it before, and I will start subtracting points if you use incorrect notation. So U, the way we can write this is that it's the span of one vector, the 1, 2 vector. Since it's this x2x can be written as x times 1, 2 vector, where x is any real number. And actually we use the notation that span, it's a list, but right now it has one vector in it. Similarly, W is the span of the 1, 3 vector. Now if we want to add together these two subspaces, please look up again the definition of how to add together subspaces. The definition was that it's all the linear combination, all the possible linear combinations of the vectors in U, for example, C1 times 1, 2, plus vectors from W, let's say C2 times 1, 3, where C1, C2 are real numbers, because we look at the real scalar field. Then note that this is the same as the span of the vectors 1, 2 and 1, 3, the list of vectors 1, 2 and 1, 3. Then if you have two vectors in R2, actually two vectors in any dimensions, if they are not collinear, that means they are not in line, that means that they are linearly independent, or they form a linearly independent set or list. Another way to see linear independence that I also want to emphasize is using the reduced row echelon form. Don't use determinants right now because we didn't cover it. I never talked about determinants so far in this course. The reduced row echelon form, you have to work it out, and on the homework you have to show your work. 1, 0, 0, 1, the matrix. So you have two pivots, and that means again that the list of two vectors is linearly independent. Because these are linearly independent, that also means that the U intersection W is just the 0 vector. Of course, you can see that also from the picture and from basic algebra. So from these two properties, we get that this is a direct sum. U plus W equals R squared. And then we can define the projection onto U along W, which is from V, that's now R2, into U. Let me emphasize this is onto and along W. In fact, the book mentions that instead of along, you can also say parallel. So that geometrically that means the following. If you have here a v vector, an arbitrary v vector in R2, then we want to project this onto U parallel to W. So we draw a parallel line with W, and wherever this parallel line intersects U, that will be the image of V under P transformation. So this vector from 0 to this point is PV, and then we can similarly project V onto W parallel to U, and then we get the vector PV, but this is, so I have to be more precise, this is the projection onto U along W, and this one is the projection onto W along U. And what this says with these parallel lines, actually what you get is the parallelogram law to add together vectors. So the V vector is the sum of these two vectors. And the way you add together the two, that you shift one parallel to itself so that its starting point is at the end point of the other. Okay, this is one thing to see this from the picture, and you have to then believe me that this is really what it is. If you draw these parallel lines, the definition doesn't really say that. In fact, the definition doesn't even give us a formula. So the question is, what would be the formula for calculating P? So we want to calculate for any V vector in R2. So the way we write usually the R2 vectors is the X and Y components. And then we want to write this V as a sum of U and W vectors, and U vector is from U subspace, W vector is from the W subspace. And that means that we want to write the XY vector as, let me now denote the coefficient Cu for the U vector basis, and for the W, let me use the coefficient Cw times 1, 3 vector. So right now, V is given, the 1, 2, and 1, 3 vectors are given, and we want to figure out what Cu is. That will be actually this whole part will be the projection onto U along W. And once we know what Cu is, then we multiply it with 1, 2 vector, and we get the projection. And then, of course, we might as well calculate what Cw is. So this is actually a linear system of equations. We can also write this as a 1, 2, 1, 3, then Cu, Cw, column vector, equals to xy. So we have to solve a linear system. You have to use reduced row echelon form of the augmented matrix. This is now not a homogeneous system, so we have to solve for any given xy vector. So we solve it. How do you solve it? Using the Gauss-Jordan elimination. This is the pivot now. R2 row will be R2 minus 2 row 1. That means we get 0 here, 2 minus 2, we get 1, and this will be y minus 2x. Then we continue with the second row, and we go backward, and we make the entry above 0, so it will be row 1 equals row 1 minus row 2. So that's 1, 0, this is x minus y minus 2x, 0, 1, y minus 2x, or 3x minus y, and this is y minus 2x. And since the first column corresponds to Cu coefficient, and the second column corresponds to Cw coefficient, what we obtain is that Cu is 3x minus y. We also obtain Cw, but let's not worry about that. Since these are long calculations, let's just calculate with Cu. So then we get the projection onto U along W will be P. Well, if you apply it to V, that will be Cu1, 2, the U component, which is then 3x minus y times the 1, 2 vector, and that's the 3x minus y, 6x minus 2y vector. So this is supposed to be in U, and it is in U since a scalar multiplies this 1, 2 basis vector of U. Then, for example, we can show linearity, which was the first property. Well, we already showed that this is actually projection. We define this projection, but actually I want to practice the calculation of linearity. I want to go through this using the formula. So we have to show that for all v1, v2, v vector, which is now R2, for all a1, a2 real number, p a1, v1 plus a2, v2 is the same as a1, p v1 plus a2, p v2. Let's show this. So we start with this part. What we have is that if we write a1, v1 plus a2, v2 as components a1, x1, y1 plus a2, x2, y2, then we multiply and add component by component, so we get a1, x1 plus a2, x2, a1, y1 plus a2, y2, and then the projection onto u along w of this vector is, well, let's see what it is. It's 3x minus y and 6x minus 2, or if you want to use the scalar version, 3x minus y times 1, 2 vector. So this is now the x part, this is now the y part. So we need 3 times the x part minus the y part, and this scalar is supposed to multiply the 1, 2 vector. Then we look at the other side. Unless you want to multiply this out and simplify, there isn't much simplification since we have x's and y's combined with a's. So instead of that, let's now go to the right hand side. a1 p v1 plus a2 p v2 equals, according to the definition, it's 3x minus y, the projection. So this v1 has x1, y1 coordinates. So this is 3x1 minus y1, and then the 1, 2 vector. And then the second vector is a2 times the projection of v2 is 3x2 minus y2 times the 1, 2 vector. The 1, 2 vector. Well, then what we can do is factor out the 1, 2 vector at the end, and then multiply through to get here 3a1x1 minus a1y1 plus a2, 3a2x2 minus a2y2. And then the best way to check that this is the same as the other is that you further collect terms and factor out. For example, 3, since we need 3 in front, so we got 3a1x1 plus a2x2, and then we are left with minus a1y1, and we factor out the negative, then we get plus a2y2, multiplying the 1, 2 vector. Then we compare and see that these are the same. So this proves linearity, which was the first property. Let's look at the idempotent property, for example. Well, what we have is that for all v, which can be written as xy vector, because we are in the R2 space, we have that pxy is 3x minus y times 1, 2 vector. So we have to apply p again to check p square. For that we have to multiply in actually component by component 3x minus y and 6x minus 2y. So this is now the first component is my new x, and second component is the new y. So when I apply p square to xy, which means I apply p to pxy, that means I have to apply p onto this vector 3x minus y, 6x minus 2y. Then the definition of this is that it's 3 times the x part, which is 3x minus y, minus the y part, which is 6x minus 2y. So if I denote it with x tilde, the new x and y places, then we have here, this is x tilde and y tilde. So it's 3x tilde minus y tilde. And this is supposed to multiply the vector 1, 2. Now if you do this algebra here, you get 9x minus 3y minus 6x plus 4y. And it turns out that this is exactly 3x, 2y. So minus 3y plus 2y is minus y. And then we compare the previous one with this one. So we see that really p squared xy is the same as pxy. So we have that p squared equals p idempotent. What else can we show? Well, we can show all the other properties. Maybe let's show property 4 that says that W is null space. We have to show both directions for that. Again, want to show this part. Then we start with W vector from the W space. We have to go back and see what the W space was. The W space was the span of 1, 3 vector. So W equals to some C times the 1, 3 vector for some C scalar. Then we check what the effect of the projection is on this W vector. So that's C, 3C vector that we apply P to. That means this is my X, this is my Y. And the definition of P is, let me use the notation, X tilde, Y tilde. So this would be 3X tilde minus Y tilde, and then the 1, 2 vector. But X tilde is C, so this is 3C minus Y tilde is 3C. That means we are multiplying with 0, the 1, 2 vector, so this is the 0 vector. So PW equals the 0 vector. That means W is in the null space of P. And since this is true for all W, because we didn't specify anything special, this is true for all W vectors from the W subspace. That means the W subspace is subset of the null space. The other direction, we start with a vector from the null space of P. Let's see that this is V equals to xy, all we know about it. Then since it's in the null space, we also know that we get the 0 vector if we apply the P projection onto it. And the P projection has the form 3x minus y times the 1, 2 vector. So if this is the 0 vector, that means 3x must be equal to y, because 3x minus y must be equal to the 0. That's the only way to get the 0 vector, because 1, 2 is not the 0 vector. So that means that the scalar must be the 0. That means y equals to 3x, and then that means that v has the form x 3x, which can be written as x 1, 3. And if you look at the definition of the W space, this is in W since it's a scalar multiply of the 1, 3 vector. So we obtain that v is in W if v is in the null space. That shows that the null space is a subset of the W subspace. And then A and B together implies that the null space equals to the W. I think I'm going to ask you to show all the other properties and 4 different but similar subspaces of the R2 Euclidean vector space. It's basically just working through the definition, doing pretty much the same thing as we did for the general case, the abstract case, but now we have to apply it to a special vector space with special subspaces.